Our next speaker is Professor Mark Balas from Texas A&M University, who is a control systems expert in adaptive control systems and has made a lot of contributions for linear and nonlinear systems, control of large-scale systems, infinite dimensional systems. His area is adaptive control, and we have been collaborating on applications of his techniques, control system in Hilbert space to set the stage for the first use of adaptive control on quantum gates in quantum information systems and quantum computing. Go ahead, Mark.
Okay, thank you. Thank you, Marco. Um, I'm very happy to be part of this workshop and glad to be invited. I'm so sorry I can't be there. I am going to be at Caltech in about another month in July. So if any people are still hanging around and you want to argue more about all of the exciting things we're learning here, please go ahead. So if you can see my first slide, it says closed form Hilbert projections for quantum state observers. It sounds kind of fancy, but on it, I put some of my former students and current students, and Susan Frost at Ames and Tristan down at AFRL, and Vinod there at JPL, and Mizon, who used to be mine, but he is now in MIT. He might be out there in the audience somewhere, maybe in the distance audience. And Razad Sultani, who is the current graduate student working on the very thing that Marco just described about quantum circuits and things to do some of what we're talking about. I'm not really going to talk about that in any detail, but I just want to give you a sort of a picture of what I'm thinking about these days. Like a few of you, Farbod is one of them, and Marco is one of them. I want to join quantum systems and estimation and control theory. I really do want to see that happening. I'm sneaking some of that stuff into my own control courses here at Texas A&M. Mostly, unless my students are intrepid, they try to ignore it as they possibly can. But I hope to do better with that and would like to have a full-blown course that sort of is an introduction to quantum mechanics for controls people, intrepid ones. I would like to be able to do that. One thing about this kind of connection is it's highly likely to be a beautiful disaster. Who knows what the voltages are on either side of that connection? So I think we've had lots of beautiful disasters. They do turn out to be important. And where I think things are missing, and we heard a little bit about this already from our other speakers, from Spiros, is that we need quantum engineers. We're going to have people who are graduate students, postdocs, and finally young researchers in various places who really know something about quantum systems. And I'm leaning away from a thing that you sometimes see when there's an application area and kind of tending to think, oh, quantum systems is an application area for control. And so we just get some models and we start plugging our favorite control things into them and everything. I'm not the least bit interested in that. I think that quantum systems is a bigger deal actually than control theory. But certainly, you know, they deserve to be more or less on the same shelf when this is all over with, and that there should be ability to move back and forth between them by the people. We may not be the experts in this. We want the quantum experts to help us and tell us how to think about this and what to do. But I think it's important for those of us in the control and estimation area not to just sit back and say, well, you know, let's put it all in a Hilbert space and it'll all work. Although what I'm going to talk about is putting things in a Hilbert space. We have Professor Feynman to blame for a lot of this, I think, because years and years, I'm more than probably 50 years ago, he made this statement in some of his talks and things about how a quantum computer would operate differently from a classical and how it would actually use, you know, actual small quantum things. By the way, I guess you can't see my picture, so I'll try not to wave my hands around and do that because you can't see me, which is fine. I don't know if there's any way to turn on the Is there any way to turn on the video? Maybe there is. Oh, if only everything else was as easy as that on this stuff. And I think, the idea that this is that we're looking at what would be quantum gates. Not everything is a quantum gate in quantum computing, but that these are unitary, reversible gates, and that the circuits themselves have to be programmable ultimately, so that they are that they're reversible, and so that the information in them will be reduced, and some of it will be lost, but so that the major parts are not destroyed if we try to look backwards through the gate. And of course, we do have to deal with entanglement. Everybody's talking about it now, which means that in some sense, the wonderful ideal system that we're interested in, the quantum system, whatever it may be, if it's a hydrogen atom, or if it's a whole bunch of things, a bunch of atoms, or a single atom with lots of abilities to do things, lots of levels, energy levels and stuff. But if we're going to be able to do anything with them, they have to be embedded in an environment to some extent. And I do want to mention that environment before I finish this talk. Probably not able to give you a bunch of details about what I or what my group or what other people are doing in this, but it's well worth looking into and seeing. The big effect on the environment is information goes into the environment and you can't retrieve it. It may still be there, but we can't get it back out of the environment. And the way environments are built, the fundamental models of them are to some extent dissipative, and though they maintain some of the quantum stuff, but they aren't unitary, and so you can't reverse and get this stuff back. People sometimes call this decoherence, and maybe it's called other things and other things. Just listening to John Clauser's lecture and mentioning Richard Feynman, it maybe wasn't the greatest idea to go to his office and talk to him about this. Maybe back in the day. These days we're probably pretty safe. But it sounds like it could be a pretty exciting moment getting thrown out of his office. I guess for John, that was probably a great moment that caused him to do so many of the great things that he did do, and gave him the Nobel Prize. I want to start with what I think is the math baby talk here, and forgive me if it's baby talk for some of you, but for a lot of people it's maybe not. Is we all know classical probability in one form or another, an event space, which is a sigma algebra of these subsets that we call the events, and a probability measure, and it really is the measure theory operating on these entities that gives us the probability that we think and talk about, at least the generic probability. And one of the most fundamental theorems is Bayes' theorem, that says essentially, if we're looking at A conditioned with B, okay, that it is related to B conditioned with A, and that really there's just a scaling by the probabilities of A and the probabilities of B. In the standard classical and the Kolmogorov picture of things. Kolmogorov wrote a wonderful, very tiny little volume on all of this stuff that really is loaded with great things. But that's one picture. But another picture is the quantum probability picture. And there the event space could be, well, maybe I could get into an argument with John Clauser about this, but I'm just going to stick with the Hilbert space, a separable one, and the events are considered closed subspaces. And this is mostly me kind of leaning toward the real experts, who are Paul Dirac and John von Neumann, and hoping they'll protect me if it turns out we're all wrong. Okay, so, but usually this would be done in infinite dimensional spaces for quantum mechanics, because most of the stuff involves partial differential equations and things. But here we'll use a pretty standard CN, usual finite dimensional space that a lot of this is posed in, just to make it a little easier to pick out the pieces and understand. I hope you're able to see my cursor as it's wandering around in this thing. And so we have an inner product, and the inner product generates a norm that we would measure distances and lengths of things in. And we have an orthonormal basis. Could be finite dimensional, in this case it is, or it could be an infinite dimensional orthonormal one. So not that part is not the biggest change in the world. And mixed quantum states are thought to be superpositions of what are called, the Fiques are thought of these pure quantum states. They're the pure ones. They're the ones that can exist. And the mixed ones are maybe the ones in Spiros's talk where he was talking about the mixed universes and all that kind of stuff. But they are superpositions and superpositions of these quantum states, these pure states, and so considered mixed. And when we look at their norm squared, we would like certain entities here to turn out to be probabilities. So we want the norm squared of these things to always be 1. In other words, we should, when we're talking about this, it's not every point in the Hilbert space. It's only the points on the unit sphere that are the initial building blocks of these things. And quantum probability says we want to look at the probability, or we want to create the probability that a mixed state will collapse into one of these pure quantum states that it's made from. And that probability is the magnitude of this inner product coefficient here squared. And that can also be seen as the norm squared of this thing. Just think of it as a projection onto the space spanned by the phi any one of the particular ideal states. Okay? And that's how you get probability here. Okay, and that probability is very different from the classical probability, even though some things are carried over, and people are certainly examining all the connections and things. I imagine there are going to be thousands, millions of papers on that. Good deal. But the probability itself does behave in a different way if we accept this as the foundational quantum probability. Observables are self-adjoint operators on this Hilbert space, and the real dynamics are produced by the Schrodinger wave equation. And here, we'll let the Planck constant just be, we'll be in a coordinate system where we can just call that 1, so we don't have to keep bringing it back up stuff. And I think I tried to do that throughout just to slightly reduce the clutter. Okay. So we also have to think about how to do measurement in this space. And this is usually called POVM, positive operator valued measure. And what it really means is there's a density. We'll talk more about the density in a moment, but and there's some kind of a measurement. And the idea is that the measurement is related to outcomes, and there's a set of outcomes. Could be a finite set of outcomes, could be an infinite set. I suppose it could even be an uncountable set. That could make some exciting issues about measurement, but it might turn out to be needed. And the measurement operators then are indexed by those outcomes, okay? And they're self-adjoint, okay? They're what the physicists call positive and what the math people call positive semi-definite, but essentially they mean that the eigenvalues of the self-adjoint operator are real and they're greater than or equal to 0. So they could be equal to 0. And we want the sum of all of these measurement operators to add up to the identity so that they cover the Hilbert space that we're looking at our dynamical problem in. And then the probability of obtaining output, of collapsing into output omega out of the big omega set here is really just the trace of the density operator against the self-adjoint operator here. That's the measurement operator. Now, I know it's much more complicated than, and that there's vastly more problems in measurement, and we've got the uncertainty principle, all the rest of that business and everything. And I'm really just talking baby talk here and hoping that that will help to explain, well, part of the things we're trying to do. It's okay to be a baby now and then, or maybe just growing up from a little baby to somebody who falls and crashes into coffee tables and stuff like that. You know, that's not a bad thing. When my daughter was doing that, it was not entertaining, but it showed me, wow, this is so wonderful how quickly you realize don't get near the table. So maybe that'll help us too. So anyway, just some things about that. Let's see, I jumped too much. So quantum statistical mechanics could be phrased just in this relatively simple way, is we're looking at ensemble behavior from multiple experiments. And the quantum density operator, just for my talk, will sit in a finite dimensional space, which is the, n by n complex matrices with the Hilbert-Schmidt inner product. So the trace of rho star with rho 1 star with rho 2. Okay, just think that inner product space could be, our density space. And these density operators carry all the probabilistic information. So they carry all the probability information, not just one set of them, but they carry them all. And in many cases, in quantum information theory, they are thought of as the quantum states. And they have defining properties, and their properties are this: as operators on in that n by n space, or as matrices, or as operators on the Hilbert space. They're self-adjoint, okay? They're their own adjoint. They're positive semi-definite, or positive if we want to just easily call it that. And their trace should be 1. Their trace of these should be 1. And then a mixed state is a linear combination of these pure state projections, okay, and the mixed states. And these are the things that we're going to look at their dynamics, or we're interested in their dynamic behavior. So just like in classical mechanics, if we don't have something like Newton's equations or Lagrange or Hamilton or something to tell us about the dynamics, we're out of luck. We can't really say much about what things are going to do. And so this quantum master equation is kind of a little upgrade of the story for density operators, but it really is Schrodinger's equation with maybe a new, with maybe a new hat on it. And we're looking at ensemble averages and stuff. And so what we're going to assume is that we would be able to get access to, as functions of time, average values of certain observables. Call them all C or C1, 2, 3, or whatever. And the way then that their values are obtained is they're obtained by this following operation: trace, which is a linear operation, but then the product of these two operators, which I suppose we could certainly say, as Spiros did, that this is nonlinear. Okay? And so, this is going to be what our dynamic systems of interest are more or less going to be. I think, again, this might be baby talk for some of you, but all the density operators, remember, they're these n by n complex matrices. They're self-adjoint, they're positive, their trace is equal to 1. And it does turn out that if their trace is equal to 1 and all the rest is true, their trace of array squared is less than or equal to 1. So they all live inside the unit ball in C n by n, okay? And one easy theorem, lots of people have proved it in various ways, but it's kind of easy to prove, is that this set is closed. In other words, any kind of approximating limiting thing can't get outside of the set. If you're approximating things inside the quantum density operator set, you're going to stay in quantum densities. Okay? If you're outside in the Hilbert space somewhere else, maybe not. Or if this rho k gets outside of that space, outside of this density set, then you're not estimating densities anymore. Okay. Okay. So, and the other thing is convex, meaning that all the straight lines are going to stay in. So any straight line between two density operators is also going to contain densities in it. So that's a nice piece of things to know. So look back at the dynamics. And all of us in the controls world like to do that a lot of times, and sort of think of it as a box with maybe initial conditions coming into it and with measurements coming out of it. These are idealized. I know that there's a lot more to this just than what I'm going to say, but I'm trying to condense it down and just stick with sort of the basic pieces here, and get along with that if we can. And so we could think that we have several of these things. Maybe there's an infinity of them, but mostly right now we're in finite dimensional space. So let's think there's a finite dimensional collection of these observable operators that are going to work on this density that can move around in time. Okay. And we'll think of H as the Hamiltonian energy operator that describes what's going on here, basically what's going on. Getting access to some of this stuff is really very difficult. I just want to sort of show you some pictures of things. One route you could take is you could just come along and you could say, hey, it's a dynamical system. I could vectorize this operation. Physicists call these super operators because they're operators on operators, but we could vectorize the density operators from a matrix into a vector just by stacking their columns and things. And we could make this into a relatively big finite dimensional system with, vectors and matrices and things in it. And then we could turn around and say, well, let's assume that the outputs are noisy in some sense, okay? Typically Gaussian or white noise or some kind of things like that. And then we could plug in the Kalman filter, the ever-ready Kalman filter, and we could say, well, let's hope everything works. Our difficulty there is that all of that is very nice and everything until you start talking about what is the noise. And the quantum noise is nothing like any of this stuff. Sometimes it's used as Gaussian noise just as an approximation. But it's very different. And in fact, all of these operations are somewhat different too, and they make things different. So, we're going to try to live with that, try to just stay within that. Sorry for jumping. One thing to notice is that what we said before is the density operators form an invariant set of this dynamical system. If you start in it, you stay in it forever. So once a quantum density, always a quantum density. But if for some reason the dynamics leaves this set, then you're not working with a quantum density operator any longer. Right? So here's that picture of that. I would like to say, just think of some kind of thing here. This is just the way we frame it, of a linear quantum density estimator. Okay, and it is somewhat nonlinear here. It's going to get truly nonlinear in a moment. But let's just think there's a linear density estimator for this dynamical system. But we cannot guarantee that even though we may start initially, our system starts as a density. After all, if we're measuring a real quantum system, somehow it must have started there. But that our picture, this leaves the density. This leaves the density operator system. And so rho hat with error is not a density anymore. It doesn't necessarily have trace equal to 1. It isn't positive. All of those things, okay? All of those things. And so it doesn't remain a density. How could we keep it in the convex set? What would we do? How would we change or modify this thing, this algorithm or whatever they were? Well, Hilbert described this thing and said, there's a way to create a projection onto a closed convex set, which luckily the density operators do form, and that we can get this projection to be the minimizer, okay, of the distance from wherever we are in the Hilbert space to the projection into or onto the density, into the convex density set, that minimum thing. Here's properties of projection. Some of them have been proved by other people. But it's a well-defined thing. If you're in the set, the projection doesn't do anything. You do get idempotentness. In other words, project twice and you get the same thing. Here's a sort of principle of orthogonality that comes along here. It's not quite the same, but it is there. And here's probably maybe the most important thing about this thing. PS is not linear. It is not a linear operator, but it is Lipschitz continuous. Okay. It is Lipschitz continuous. Okay. In fact, it's non-expansive. Okay. It's not contractive, but it is non-expansive. Okay. And that is a big help. That tells you something about the smoothness of this thing. And so what we're speaking about here is taking the picture we showed before and adding a nonlinear projection operator. So now this produces essentially an attempt at doing things more or less linearly and more or less the way you would do them in a quantum control, in a control picture, but adding this projection, this nonlinear operator to it so that rho double hat stays inside. It is a projection, it is a density operator no matter what. Okay. And that's done because that happens because of the Lipschitz behavior of the projection. Okay. Even though it's nonlinear. Okay. And so this can be very helpful because many times when you're doing approximations, you don't get everything right, and things may leave the set of density operators. Kalman filter just by itself wouldn't necessarily stay inside of this thing as it doing its estimates. It's a minimum variance kind of thing. So, you know, here's kind of, it seems simple-minded, but I think that's what ideas at work are actually simple-minded. That's part of the beautiful disaster, I hope. And so, okay. And we could do this. Sorry, let me go back one. So we could think about doing this in that finite dimensional space and all that sort of stuff. But actually, we can also do it in the full infinite dimensional quantum systems that we would have to know about, where we have a poorly known Hamiltonian, perhaps, and some other issues. And so it may take some work for us to develop the measurement part of this thing and the POVM and so forth stuff, but it's possible for us to have an adaptive quantum state estimator and add to it the nonlinear density projection, okay, and be able to do the picture we saw before, and in fact be able to get in this case asymptotic, and in the case before, in this case here, be able to get exponential convergence, okay, in time. Okay, so being able to do this either over a bunch of data, over a large collection of data, or being able to do this over an ergodic collection of measurements, that we would be able to get good convergence. Here, only asymptotic, but that's surely better than a lot of things. Okay, and so here's a couple of the metric projections things. They're really easy to do least squares with closed subspaces. You just use the metric projection on the closed subspace with orthogonal vectors spanning the closed space. That's easy to do. It's fairly easy to do the unit sphere, because what you have to do is take anything that you get as a state and divide it by its norm. Okay, and those things can be done. You can use the projection on a hyperplane. Okay, and here's a way to do this along the hyperplane. So, and I'll just mention that, and here's a way to do over a closed cone. The cone is probably more what we would think about using here. A cone is where any positive linear combination stays inside the cone. Okay, and we could maybe do it. And I'll just mention that in one of our papers, the ACC 2023, Maison and I and our colleagues did develop a closed form thing for quantum observers. So there is a way to do this in a closed form. A lot of the problem with the projection is how to actually do it. You know, how to actually make a working algorithm to do it. Okay. Quantum information theory developed sort of out of Shannon's classical information ideas and stuff, and developed directly from this idea of the Shannon entropy. But my understanding, just because there's gossip and all this sort of stuff around, you never know if it's all true or not, is that Shannon talked to our main person over in Hilbert space, okay, von Neumann. And von Neumann said, "Oh, I don't know, you might try this." Well, you know, if von Neumann tells you something, you're a fool not to try it. And so, well, however this really came about, it doesn't matter. It doesn't take anything away from what Shannon and everybody else in information theory has done. But to see it this way as the average amount of information gained from learning the value of a random variable x, or the average uncertainty before you learn it, okay? And here's the quantum von Neumann entropy, okay, for this thing, which, look, it's this thing. The minus sign is just because of the log thing. You probably put a minus sign in here too. But you take the trace of the density against the log of the density, okay? And the nice thing about that is we can do the same things we talked about before and get asymptotic convergence, okay? Not exponential, but can get asymptotic convergence. So we can use those estimators we spoke about and close in on the von Neumann entropy. Everybody puts in controls puts in a little example. We did a bunch of examples in QSID as well, and Merzad has done all that stuff, but just mention one to show that there's an example. Here we vectorize this thing, vectorize the master equation and stuff, so we could work with it in a little bit in MATLAB and so forth things. But just to see, here kind of what happens inside this thing and see about the convergence. Yes, we do get, it is exponential in this case. Let's see what happens when we go. I think, is that all we need? Yeah, maybe that's enough. That's enough of examples, but there's a bunch of QSIT ones that I would love to show you. I will maybe put something together later on. So time behavior is an important piece here. And the stuff I just talked about is like the system that we're interested in is completely ideal, and it exists without any connection to anything else. It's the ideal system. It's the hydrogen atom or whatever it is, but it's whatever quantum system it is, okay, or that we're modeling here and stuff. And then we have that the evolution is always unitary. In other words, you always stay inside the unit ball, and you always are a density operator here. Open systems are in the quantum world. And of course, that means that in some sense, they end up being entangled with everything. Maybe in a very mild way, maybe in a very strong way. Some of this is, of course, still under debate, as John Clauser said in his work and stuff. So, a lot of this is still to come. But just to think about, what does it mean to be an open system? Well, we have what we would call a master equation here. And we have the basic system, this guy here. We have the environment, some kind of a model of the environment, okay? And then the interaction of the environment with the basic system. And we could treat this as that the basic system and the environment interact with each other. Most stuff right now that people are talking about is based upon the Lindblad point of view and Lindblad operator. And here's a picture of it for this thing. Here's the unitary part of it. And over here, these are called the jump. These operators, they're named after Lindblad to some extent, and are they the jump operators and things, and they are dissipative. What they do is they maintain the traces of zero in here. They maintain complete positivity, which is an important quantum thing, but they don't maintain unitarity, and they are dissipative. And so this is more of the environment taking information away from the ideal system, okay? And being able, and what I think a lot of other people would like to do is look more at measurement and things where we are looking at open systems, and that we can see these things with, it isn't going to be perfect, but we can see it with relative capability, and be able to make distinctions in this, and at the same time maybe even use the entanglement to make life better, right? Now I lost track of time, and if I'm over my time thing here and everything, I'll try to quickly wind up. But I'm just saying that, there are all these places where there's more work to be done, and also, of course, the building of these. As Spiro said, the building of these things. We're nowhere near the level of things we need to make quantum computers do what we hope that they would be able to do. But some of this can be folded into the mathematical picture, I think. And here's some of the things that one might look at. Quantum semigroups, even random matrix theory is kind of a little hot topic right now, of people looking at some of the behavior of open systems with random matrix theory and stuff. It does sort of give different pictures of things. There's a lot of things that could be done here with quantum semigroups. Here's just my wild dream, but it's probably everybody's wild dream in some form, is that we could have an open system and we could use some kind of adaptive, but quantum adaptive way of looking at the difference between a relatively decoherence-free, maybe it would have an environment, a Lindblad in it to some extent, but we could use this sort of the pure version. Purified is not the right word to use and mean something different in quantum, but the pure version of picture, and we could compare them, and we could try to reduce decoherence. This would happen as we allowed the measurements to move in time, things, whether that was the Heisenberg picture or whether we use the the shorter one, but we would do that. Okay, and that there could be an adaptive. Pieces of that, the observer stuff that I showed you are certainly pieces of that. Here's a thing that that Marco wanted me to say something about, and I thought this will get me in more trouble than anything else that I've said. So you know, I want to find out where John Clauser lives and see if he'd take me in and keep me in his basement, you know, while all the terrible things are happening, and again, we would be protected from the heresy. But this is, are there other systems that are quantum-like? In other words, that their probability description behaves like the quantum thing and not like the classical one. And cognition might be one of those things. Now, I think as a model for human decision-making, it requires a very experienced operator to be interfacing with a very highly well-designed cyber system, okay, whatever that may be. And again, none of those things are around. Jim Hubbard and I have been working on this. He got me involved in it, for better or worse. And we've had a few proposals turned down, but the one that was the most deeply cutting is they called us hopelessly naive. And so Jim and I invented the Center for the Hopelessly Naive at Texas A&M. You're welcome to join if you want to. And there's a place where, you know, we might all be protected, even though we might be living in John Clauser's basement. Here's some of our papers and things that are more current now and that are around. That'll be attached to this thing. I'm assuming that we'll have some version of this that's available after the show. Here's a thing that I like to end with. That this man is a poet, was a Lisbon poet. He was actually quite well known. But here's a statement that he made about, he was making a mirror about literature and poetry, but I think it works very well here. No intelligent idea can gain general acceptance unless some stupidity is mixed in with it. So that's Fernando Pessoa. You can read that in the Book of Disquiet and everything. And the way I look at this is, I hope I've been doing my part in including enough stupidity in what we're talking about here so that we'll find an intelligent idea that gets general acceptance. And I thank you for your kind intention. I can't hear your applause, but I'm grateful for it.
So we're a little bit late for the lunch break, but
yeah.
Perhaps only one question before we break. Maybe we can. Yeah, we can do that later. Thank you, Mark.
Just put it in the Q&A later. I'll come back.
Yeah, we can in the Q&A. So
okay.
We're breaking for lunch, and we are resuming at 1:30 in the Firestone. Let's see. No.
Firestone Laboratory.
Firestone Laboratory.
Yes.
And the number of the room, 340. 340.
Third floor.
Third floor of Firestone.
And there's a sign on the door if you'd like to join.
Yeah, so we'll meet there at 1:30, and now we're breaking for lunch. Okay.
Thank you, everyone.
Thank you, Mark.
Thank you.
How do we get out of here?
Okay.
You know,
Yes, sure.